Okay, so now another rule that will look at combinations of different functions. You probably have watched or learnt about the product rule at this point, a product of two functions. Now we're going to look at a division, a quotient of two functions, okay, which in some ways is very similar to the product rule. Okay, division and multiplication are sort of closely linked, obviously, but we're going to present it as a completely separate rule. Alright, so you see three functions here, which are in itself two functions divided by each other. Okay, one function over another function. And I will show you the derivative of these three, and you can have a think about what is the rule here. Okay, so this is going to be minus I'm going to the bottom there to have a look at the rule myself, because this is one that is quite easy to forget, or quite useful to double check if you are in an exam. Okay, so even though I've done it thousands of times, I often need a little double check about how the rule works. So that is the derivative for the first one. This will be the derivative for the second. It's going to look a little bit more complicated now. Okay, and this is going to be all over 25x squared. So I'm starting to look a little bit more complicated. And ones like this, you'll start to see get quite long and cumbersome. Okay, yeah, especially that one there. Okay, so what is going on here? Well, you may have spotted the rule below a couple of times already, and what you may have seen and you may have spotted is where all of these come from, where all of these parts come from, and maybe even this as well. So clearly 5x is just this denominator function, and you may see that 5 is its derivative. E to the power of x could obviously be the original function or its derivative. So let's look at the third one here. This looks like the derivative of the denominator. This is the original numerator. This, well, is a combination actually. It's, if I split it up, it would actually be 2x times 3 sine of x. Okay, so 2x would have been the derivative of the numerator. 3 sine of x is the original denominator. Okay, and we start to see a pattern. Okay, this the 25x squared and the 9 sine squared x seem to both come from the square of the denominator. Okay, and is all of this the same for the top one? Well, yes, I have firstly the derivative of the numerator is 0 for that one. So we simply have the numerator and the derivative of the denominator, and we have the denominator squared below. Okay, just double check this one more time. And well, we see a perfect example of how easy it is to get this mixed up. Okay, I didn't double check on the third one, and I did indeed get it the wrong way around. Okay, so I will leave this in as a perfect example of how, even though on the chain rule or the product rule, you probably, after doing it many times, you don't really need to keep looking at it, especially the product rule, which you can just reverse and stuff. It's not really a problem. Okay, but when you have a subtraction like this, it is obviously important to get it the right way around. So I would suggest in an exam double checking, because what I did there was, well, I was meant to, we can now have a peek at the rule. Okay, if we have u over v, well, the original v, the denominator, is multiplied by the derivative of the numerator, and then we subtract original numerator times derivative of denominator. And I did that the opposite way around initially. Okay, so I should have had 3 sine x, the original denominator here, multiplied by the derivative of the numerator, and then minus the opposite of those. So let's summarize this rule now that we've finally arranged our thoughts properly. And so I need this time to have a f of x over g of x, and the derivative of this is going to be g of x times the derivative of f minus f times the derivative of g all over this whole function g squared. Okay, and you can see just a slightly different version of this using u and v as my 2 functions. And that is what you'll see in the formula booklet, and that's easy enough to follow as well. Quite similar to the product rule in that you're just going to identify your f and g, or your u and v, and then identify their individual derivatives, and then all you got to do then is plug it into this quite long formula. Okay. All right, so let's have a couple of examples. So I'm going to identify my f and my g, and I'm going to differentiate them both one by one. E to the power of x stays the same, and there I have my 4 elements, and I can plug them in. So we're going to start off with g times f dash of x, then we are going to subtract the opposite of that, sorry, looks like I got mixed up again. E to the power of x times minus sine of x I should have had. Okay, g times the derivative of f. Again, you just got to be extra careful with this rule. A million mistakes you could make. And e to the power of x squared, I might just call e to the power of 2x. Okay, and there's probably some nice factoring I could do on the top, and therefore actually some cancellation I could do, I believe, but I will leave it there for now, because here I have a bit more of a challenging one. Okay, so my f is going to be 5x squared cos of x. That's going to be a little bit of a problem. G is e to the power of x again. Okay, so g dash is just going to be the same. And, okay, I'm trying to differentiate f, but I actually have a product of 2 functions. So I'm going to use the product rule within the quotient rule. Okay, and I just realized I didn't mention this is called the quotient rule. Okay, and I have a quotient, a fraction, a division of two functions. But here I'm going to use the product rule within it because I have a product of two functions as my numerator. So if you remember, I'm going to do 10x cos of x plus, or in fact minus, because cos of x goes to minus sine x, minus 5x squared sine x. And that's my whole derivative of the numerator. Now I've arranged it nicely, I can just carefully complete the formula. So original g times derivative of f minus f times derivative of g. Okay, now use a bracket for this, and well, this is going to be long. Although the second term, maybe not quite as long. All over the original g squared, which is again e to the power of 2x, e to the power of x squared. And just like last time, I could probably simplify that a little bit better if I had the time. So this is the kind of thing you get quite often with quotient rule, some quite long derivative functions, okay, which you can then use to find slopes of tangents, to find equations of tangents, normals, stationary points, inflection points, and so on. Okay, so lots of practice needed for that one to become fluent in using the rule. Okay, and probably some much more sophisticated ways of coming about the formula in the first place, okay, through various proofs and maybe differentiation by first principles with limits and things like that. Okay.